This is what our simple environment looks like. You can see the agent can only move linearly on this straight path. The agent will always start just in front of the emerald block, and its goal is to move onto it and stay there, as this will accrue the most reward. Here are the instructions for the algorithm we're going to follow. Cross-Entropy is a very simple policy gradient algorithm that just basically consists of these 5 steps. We'll walk through them as they relate to the project in the next couple of sections. Here's a clip of the agent training. You can see its Z position changing as it moves forwards and backwards. As you can see, the Z position isn't changing by a certain step size like 1 or 0.5, so we have a continuous state space. Although the Z position might be the most natural representation of the state to train on because it is the most direct representation of the state, I'm going to try something a little bit different and instead give the agent a feature vector containing the blocks below it. Although we have a continuous state space, the agent is actually going to see a discrete feature vector. And so basically what this is going to mean is that all z values between 0 inclusive and 1 exclusive will be considered the same block, and then all z values between 1 inclusive and 2 exclusive will also be considered another block, and 2 and 3, 3 and 4, so on. So, all of those states between those integer values will be considered to be the same block. And this is a simple form of state aggregation, since we're taking a bunch of states and just combining them into one, more or less. Let's hop over to Blender to see how this works. So we have our agent moving forwards and backwards as usual, and now we can see how the agent views the state that it's in, and instead of some z value, it gets a feature vector of 0s and 1s. Since there's only 2 types of blocks, grass and emerald, we can just have binary features, so either 0 or 1, and you see that 0 corresponds to grass block and 1 corresponds to emerald block. And we can see as the agent moves forwards, the feature vector only changes as the agent steps into the next block. And interestingly, with this kind of state aggregation, we only actually have 4 different possible feature vectors, as you can see here, and we can just rewrite those in their vector forms. Now let's take a look at how an agent might act in a given state. Here we have the feature vector 0, 0, 1, which corresponds to what we just saw in the Blender scene beforehand. Now we can pass the vector through the neural network, and we will get preferences as an output. And then if we pass those preferences through the softmax function, we can get probabilities that we will assign to the different actions. So the probability that we will go forwards, stay in place, or go backwards. Each episode will last for 30 seconds worth of ticks, and the agent will go through a number of state action reward time steps in that time. At the end of each episode, all of the rewards are summed up, and after 10 episodes have been completed, the episode with the highest cumulative reward will be trained on. Now that we have our episode isolated, I'm going to do 2 things. One is get rid of the rewards because they don't really matter at training time, and the second thing is I'm going to bring the state action steps over to the left here, and you see there's kind of 2 columns separated by a comma. To the left are states in their feature vector forms, and to the right are actions, which are 1 hot encoded, so that if you have a 1 in the first index of that vector, it means that that action must go backwards. If you have a 1 in the middle, the action will stay in place, and if you have a 1 to the right side, that action must go forwards. Now we can take a look at how training is actually going to work. You see we have this input vector on the left side, and we're going to pass that through the neural network, and it will give out some values, and we also have our expected output column here, which is just the 1 hot encoding of the action we should take, or should have taken, and we can just compute the error between the outputs of the neural network and this expected output and perform stochastic gradient descent to train our neural network. And we can just watch a few other training examples. Something that's important to note is that even though we have the set of inputs and expected outputs, which are just states and expected actions, those actions are not necessarily the best actions to take in the state, but just the way the episode unfolded, that's what happened. Now that we're done with the training, we can talk about the results. So the one parameter I varied in this experiment was the step size of the agent. That's not any learning rate or anything, it's just literally how far he moves when he goes forwards or backwards. And remember, this is not a discrete movement, but more like a force that's applied to him forwards or backwards. Alright, now we're going to go ahead and look at the results for step size of 1.0 and 0.5. So loss is pretty self-explanatory. Mean batch reward is just the reward of the optimal episode we are training on. And we can look down here at the future vectors, and basically what this is, the preference for the action back in the feature vector 0, 0, 0. So more or less, how much do we prefer going backwards when we are in the feature vector 0, 0, 0. And you can see here it's quite preferred over the other actions, and that makes sense because the agent starts in front of the emerald block. So if it were to at some point end up a little bit more in front, it would need to learn to go backwards then. Right here, this is when the emerald block is right in front of the agent, and you can see that back is still pretty high, and it's actually higher than these other results, and the true result here should be forwards. And just to note, this is after 2,000 training batches, so that's 20,000 episodes. Right here we have just staying in place. So we can see over here for 0, 1, 0, which is when the emerald block is right below the agent, the score for staying in place is pretty high, and it is actually higher than that value, although it is a bit hard to tell. So stay is actually what was found to be preferred here, and that's correct. And here is when the emerald block is right behind the agent, and that you can see is preferred to go backwards, and that makes sense, that's correct. So the only problem that we really run into with the one step, or the step of one agent, is that when it starts going backwards, it oversteps, and it ends up going too far, so it just sort of keeps going farther and farther, because we saw that this, if it's ever in a 0, 0, 0 position, it'll always go back. Now we can look at 0.5. And here we see for 0, 0, 0, stay was actually the preferred option. Interestingly, the only two states we need to actually learn are 0, 1, 0 and 1, 0, 0. 0, 1, 0 is when the agent is on top of the emerald, and 1, 0, 0 is when the emerald is directly behind the agent. And we can see here that we do indeed learn correctly to stay, and also back is learned correctly. So now we can go ahead and look at the agent actually acting optimally. And here is with a step size of 1, and you see it's already gone too far back, and now I'm moving it back up. And it will always just go too far back, and even though it knows it should stay on the emerald when it gets there, it will accidentally go too far back. Here's for 0.5, you see it nicely moves back onto the target, and I just moved it off. But see, it hasn't learned to go actually back forwards. Now I'm moving it forwards again, and it just hasn't learned to do that. It's only learned to move back when it's right in front of the emerald. So what we see is that the agent with 0.5 step size will always act optimally if it is started just in front of the emerald. Thanks for watching.